Well, good morning, everyone. Welcome back. I hope you've enjoyed the past week, and I hope you enjoyed the warm weather while it lasted. I mean, I know I didn't because I've been working on this seminar series, but hopefully you had some time to enjoy all that. As usual, I'm going to start out with just some admin stuff. So a quick reminder that there's not going to be any seminar next week, October 9th, because of Thanksgiving, of course. So our next seminar is actually going to be Monday, October 16th. So that's going to be our seminar on ANOVA and factorial ANOVA. And in case you didn't see last time, the link for my GitHub page where I post all the material, I'll give it here again. As I had mentioned, the fastest way to find it is just to do a Google search of GitHub and then my first and last name, and you should be able to find it right away. And so I post all the slides, including today's slides, and the tutorial material on that GitHub page. And I encourage you at any time to send me an email if you have any questions, admin questions or just questions about the lecture material. I'm happy to answer things or make clarifications for you if you need it. All right, so a quick recap of what we did in the last lecture. So we started out by defining this idea of hypothesis testing. So if we wanted to test our data, we would first have to define our parameter of interest, and we have to define how we're going to test the parameter of interest. And we categorize this parameter into two sorts of states of the world. One is our null hypothesis, so something that's not particularly interesting, and the other is our alternative hypothesis, which is usually the more sort of interesting result. And in order to do the hypothesis test, we looked at specifically how to do a hypothesis test for the sample mean. So we looked at the distribution, the theoretical distribution of that sample mean, and how to interpret what we call the standard error of the mean, this estimated standard deviation divided by the square root of n. And from there we went into our one sample t-test, so testing a mean against some fixed quantity, and we also looked at the independent samples t-test, looking at the differences between the means in two groups. Okay, so today we're going to go into linear regression. So linear regression is really a great method. It's used all the time, something that I use every single day. So this allows us to study the effect of one or more continuous or categorical variables on the mean of some continuous variable. So if you remember back to our t-test, our sort of response variable, the variable we were interested in, was a continuous variable. So that is still the case here. Our outcome variable is continuous, but our variables that we're seeing if they have an effect on the outcome variable, they can either be continuous or categorical. So we call those variables our predictor variables. And today I'm going to focus on the case where we have a continuous predictor variable. And so the point is, we're not looking for any sort of exact relationship. Of course, there's probably not going to be an exact linear relationship between two variables, so we're only modeling the mean of our outcome continuous variable. And as it turns out, a lot of what we do, a lot of our statistical methods turn out to be special cases of linear regression. So what we did last week, our one sample and independent samples t-test, and what we're going to do in our next lecture 2 weeks from now, the ANOVA and the factorial ANOVA, these are all very special cases of linear regression. Now, we talked a little bit about the assumptions we made last week when we did the t-test. And again, today we're going to talk about assumptions, but the assumptions in linear regression usually take a little bit more attention. You need a little bit more care when you're doing linear regression. And so I'm going to show you some methods for checking assumptions. All right, so the general idea of linear regression is Well, as I said today, I'm going to focus on the case where we have a continuous variable versus a continuous variable. So here I've plotted some data from my favorite online resource, the International Mouse Phenotyping Consortium. And so I just have some clinical blood chemistry measures. I have creatinine and total cholesterol on the y-axis. And what we're looking for is we want to see if we can find some sort of general linear trend between these two variables. And as you can see, it looks like, it doesn't really look like this data falls on a line whatsoever. However, as I said, we are only modeling the mean of this y-axis variable. So we're only looking at the mean of total cholesterol as a function of creatinine. So before we get into linear regression, I'm going to talk about something that most of you are likely already familiar with, and that's this idea of correlation. So this is a very popular method of measuring the association between two continuous variables. It's also known as Pearson's correlation coefficient. So the notation is going to stay very similar to what we had before. So we have n samples, and this time from two variables, x and y. So x, you have samples from our n individuals, x1 through xn. And on the y variable, you have the y variable measured on those same individuals, y1 through yn. And we can calculate this big kind of ugly formula, which is the sample correlation coefficient. And we call it R by convention. And what we see in the numerator here, so we see a sum over all individuals, and we see something that looks a lot like a term, a quantity that we had in our sample variance. So we had xi minus x bar squared before. Well, this time instead of squaring it, we're multiplying xi minus x bar by yi minus y bar. And the reason we do this is it turns out that if x tends to increase when y increases, then you're going to end up with a positive quantity on the numerator. And if there's an inverse relationship between the two variables, if when x increases, y tends to decrease, then you're going to get a negative value on the numerator. And so that means that if there is a general positive relationship between these two variables, then R is going to be positive. And if there's an inverse or a negative relationship between these two variables, then R is going to be negative. And what we see on the denominator, this is just basically something that looks sort of like the sample mean of x, and something that looks like the sample, or the sample variance of x and the sample variance of y under a square root. And all that does is it just scales down the correlation coefficient so that it has kind of a nice interpretation. So let's go into that. So when we scale this coefficient down, turns out that it falls between the values -1 and 1. So just a recap, if R is greater than 0, then we have a positive association between x and y. So as x increases, y tends to increase as well. And if R is less than 0, then we have a negative association or an inverse relationship. If R is equal to 0, then things get a little bit more complicated. We can't say a whole lot about the relationship between the variables if R is equal to 0. The only thing we really can say is that we have not found any sort of apparent linear relationship between these two variables. And the word linear is very, very important when we're looking at Pearson's correlation coefficient, because correlation only measures whether there is specifically a linear relationship between the two variables. So you could have a more complicated nonlinear relationship where the two variables are very, very strongly related in that way, but you end up with a small correlation coefficient. Now, if R is equal to 1 or R is equal to -1, so on either bound, then this would imply either a perfect positive or negative linear relationship between these two variables. So if you imagine r is equal to 1, that would mean that all of your points are going to fall exactly on a straight line. So here's just a kind of visual of what I just explained. So here's the case where we have a positive linear association between x and y. So you're going to get r as a positive value. Here in panel B, we have a negative linear association between the two variables, and so we're going to end up with a negative value of r. And in the 3 panels in the bottom, these are 3 separate cases, 3 very different cases where r turns out to be 0. So in the first one on the left here, we have a case where the 2 variables are actually independent. So the values of one variable do not give you information on the value of the other variable. And in that case, if the variables are independent, then r is going to be equal to 0. However, on the right, we have 2 cases where the variables most definitely are not independent. So you can see that there's this sort of curved relationship in both cases. But if you calculate your Pearson's correlation coefficient, you're still going to get 0 in both cases. So this just goes to show that you have to be careful. When you get a correlation of 0, that does not necessarily mean that the 2 variables are independent. That just means that there is no apparent linear relationship between the 2. All right, so the good thing about correlation is that because we scaled it down so that it falls between -1 and 1, we can compare correlations between different sets of variables or different pairs of variables. So even if they're on very different scales, we can compare the correlation from one pair of variables to another pair of variables and say, okay, these 2 are more strongly correlated than these other 2. One of the weaknesses of the correlation coefficient is that it doesn't give us any information on the effect of one variable, on the size of the effect of one variable on the other variable. Often what we're interested in is how much our y variable is going to change with respect to a change in our x variable. And in order to do this, we need to get into linear regression. And so I'm going to start with something called simple linear regression, which is sort of the most basic version of linear regression, and that is going to allow us to estimate this quantity of interest. So I'll go right into simple linear regression. So here's sort of a visual of what linear regression is doing back in our IMPC data set. So we want to try and find a best fit line to this data. And the parameter of interest in linear regression is going to be the slope of this best fit line. So if you imagine a very, very steep slope of this line, that would mean that if creatinine increased just a little bit, then total cholesterol would increase by a lot. And if the line is not steep, if the line is very flat, then that would mean that as creatinine increases, total cholesterol does not increase by very much. And I want to stress one more time that, of course, we're only modeling the mean of total cholesterol. So you can see here, on the left, there's a mouse here that has a very high level of total cholesterol, and a mouse over here which has a very low level of total cholesterol. So that goes sort of against our estimated pattern here. So really all we're doing is we're just estimating a general trend. It's not going to be a perfect model. That goes back to my first lecture where I said that really none of our models that we fit are ever going to be perfect. All right, so how are we going to find this best fit line? So here I've simulated 10 data points, pictured in blue here. And this green line is our best fit line. So if you remember back to any math classes you might have taken, there are two parameters which define a line. One is what we call the intercept, and so basically it just shifts this line up and down, but it does not change the slope of the line. And the second parameter is what we call the slope parameter, and so that is just going to tilt the line and give it a larger or smaller slope, or even a negative slope, so going sort of going downhill as we go to the right. But in order to find a best fit line, we first have to define what we mean by a best fit. There are many ways that we could do that, as it turns out, but the most common way is going back to this idea of the residual. So if you remember back to our first lecture, we had defined the residuals on sort of a flat line, on just a mean. Well, we have exactly the same quantity in linear regression. So the residual is just taking the difference between each of our points and the point where it intersects the line. So basically, you're looking specifically at the vertical distance. You're not considering the distance in x towards this line. So as before, if you fall below the line, then you're going to have a negative value, and if you fall above the line, you're going to have a positive value. One assumption that gets made when you do this, because you're only looking at the vertical distance, is that you're assuming that the x values are fixed. And by fixed, I mean that you're assuming that there is no measurement error in the x variable. Well, that's something that is probably not going to be true. And as it turns out, this is one of those assumptions that just sort of completely gets ignored. And that's something that I even do as well. I almost never consider the error in this x variable. And so as it turns out, by ignoring this possible variation in the x variable, you do introduce a little bit of bias into your estimate. However, this bias tends to be towards the null hypothesis. So by ignoring this measurement error, you are probably not going to find a spurious association between the two variables. You're most likely going to actually underestimate your association between the two variables. But yeah, so even though it's technically an assumption we make, it is probably something that is very rarely true, but it just sort of gets pushed aside most of the time. All right, so what we do is we look at what we call the sum square of the residuals. So we take each of our observed values, which we call yi, so each of the blue points, and we subtract off yi hat. So we call yi hat the fitted value, and that, as I said, is just what you get when you move each of these points vertically up or down until they hit the line. So in this case, our yi minus y hat would be minus 1.68. And so we just take the squares of all those values, as we did in our sample variance, and we take the sum of all them. And from there, we try to minimize this value. So we can play with the two parameters that define our line. So we can play with the slope parameter, making the line go up and down, and we can play, the intercept parameter where the line can go up and down, and we can play with the slope parameter, which is going to tilt the line and change the slope. And we want to find the pair of parameters which minimizes this sum square of residuals. Well, there actually is a very nice solution to this problem. If you set this problem up, you can just do some elementary calculus and you can get a nice formula for the optimal solution. And the estimator that we get for the slope and the intercept is what we call the least squares estimator. And so before I introduce that, I'm just going to show you the equation for this regression line, the way we set it up. So every single individual yi, so again, these yi's are the y values of these blue points. We can decompose it into two parts. We have b0 plus b1 xi, so that's what we call the model part. And then we have this epsilon I, which is an individual specific error term. So that's how sort of wrong our model is from the true observed value. And so our main parameter of interest is beta 1. I just realized I have a typo here. This says beta 0, B0 estimates the slope of the line. This should be B1, actually. So yeah, B1 is our main parameter of interest. That's going to estimate the slope of this line. So if B1 is positive, then you'll see something like this. You're going to have a positive slope on the line. And if B1 is negative, then that would mean you would have a negative slope for this line. All right, so we have our fitted line, and we have this error term as well. And we have to make an assumption on this error term if we want to do hypothesis testing. So we assume that epsilon I follows a normal distribution with mean 0. So that just means that we assume that the errors sort of just cancel each other out. Like sometimes you're going to get errors that are above the line, and sometimes you're going to get errors that are below the line with sort of equal chance. And we assume that each individual's standard deviation of their error term is constant, that it follows, that it has this standard deviation equal to sigma. So that's an important assumption, and all it means is that as we look at the points, how the points fall around this line, sort of the variation of the points above and below that line does not change as we change our x variable. So that just means that how good the fit of the line is on one side is the same as how good the fit of the line is on the other side. And so this epsilon I is going to contain additional variation in y, which is not explained by our predictor variable x. So that could be through other variables that have not been included in the model, or it could just be something like random statistical variation, which we can never really measure. All right, so here is the least squares estimator. So as I said, you can find an exact solution for the slope of this line. And here's the formula. And in the numerator of the formula, you have something that looks very similar to the Pearson correlation coefficient. And as it turns out, there's a very close relationship between that Pearson's correlation coefficient and the slope of this line in simple linear regression. And in this slope parameter, instead of dividing by the sample variances of x and y as we did before, we just divide by the sum of xi minus x bar squared. And so this is going to leave this parameter on the units of x and y. So before the correlation, we completely got rid of the units of our variables. Here we think of b1 hat as being kind of a change in our response variable with respect to a change in our predictor variable x. One thing I just want to point out is that I think I had mentioned this in a previous lecture, but so when I write B1 here, that means that's a population quantity. That's something that we cannot see. That is like the true linear association between x and y. And then when I put a hat on top of that B1, that just means that is the estimated value of B1 in our sample. So that's something that we can see. It's something that we get an estimate for. So once we have the value for B1, then we just plug this into this formula and we get our estimated value of B0. B0 is something usually that we're not very interested in. Usually we're more interested in the slope of that line. But once we have estimates for these two parameters, we can calculate what we call a fitted value or a predicted value for each individual. So that's what I was showing you earlier, where I was moving those blue points vertically, either up or down, until they hit the line. So the y value you get when you hit that line is your fitted value. And it's very simple to calculate your fitted values. All you would do for each individual is you would take their x value and plug it into the formula where you have your estimated B0 and B1 values, and you're going to get your fitted values for each individual. All right, so as I mentioned, B0 is there, the intercept term, it's always there, but usually we're more interested in the slope parameter, B1. So how do we interpret B1? So let's say we had two individuals and their x values differed by exactly 1 unit. So for example, we could have the first individual has an x value, x1 equals 5, and the second individual has an x value, x2 is equal to 6. So if we were to do linear regression on just say like a broader sample, so let's say there are more than two individuals, we do linear regression on a full sample, and we look specifically at the difference between these two individuals. So I'm looking at the difference between the fitted values, so y2 hat minus y1 hat. Well, if I were to plug everything into this, just using these fitted value equations that I defined on the last slide, you go through everything, it turns out that you get B1 hat. And this is going to be true for any two individuals that differ by exactly 1 unit. So I just used 5 and 6 as an example here, but if this were 50 and 51, then this would still be true. If this were minus 200 and minus 199, this would still be true. And so that gives B1 hat a very nice interpretation. And we think of B1 hat as being the estimated, the keyword being estimated because we have a hat on there, the estimated change in y associated with an increase of exactly 1 unit of x. So if we look at a diagram of this back on our simulated data, this would mean that okay, so you look at your line, and let's say our two individuals are x equals minus 1 and x equals 0. Well, that's a difference of, that's a horizontal distance of exactly 1 unit. And so that would mean that our estimated change in y variable is B1 hat units. So yeah, this is something that gives us a very nice interpretation. It's very, very intuitive. It's sort of this rate of change in y with respect to our x variable.
What if those points just don't exist in your
data? So the question was, what happens if all of your points fall within a small range so that you can't kind of look at a 1 unit increase? Well, then it's actually going to scale down proportionally, and I'm going to give an example of that later on. Yeah, thanks. Okay, so we can set up a hypothesis test for our B1 term. We can do the same thing for our intercept term for the B0 term, but I'm just going to ignore that for now because this is something that the slope parameter hypothesis test is really the important thing that you need to know. So we want to check if there's a significant linear relationship between these two variables. So the way we set this up is we have our null hypothesis is that B1 is equal to 0. Notice that there's no hat here. Remember that whenever we do a hypothesis test, we include our population parameters, not our estimated values of the parameters. And our alternate hypothesis is just that B1 is not equal to 0. So there is a positive or negative slope associated with these two variables. If you remember last time with the t-test, in order to do our hypothesis test, we had to look at the standard error of the mean. So just giving us sort of a theoretical estimate of the distribution of the different possible mean values you would get if you had taken repeated samples from the same population. So we have a similar quantity for for beta 1 hat. And it ends up being something that's not quite as nice looking, but it's not too difficult to calculate. So it just involves, again, these the sum squared residuals. So this is exactly the thing we were trying to minimize earlier. And then it just involves in the denominator our x values. So that is going to give us kind of an estimate of how sure we are in our estimate of B1. So if this standard error is very large, then we're less confident in our estimate of B1. And if the standard error is small, then we are more confident in our estimate of B1. Well, we also use a t-test, as it turns out, to do this hypothesis test. And in order for this test to boil down to a t-test specifically, we do have to make our normality assumption. So actually, when we set up linear regression, when we do that least squares estimator, we don't actually have to assume a normal distribution when we actually find the slope and the intercept of that line. But the moment we want to do a hypothesis test, that is when we do have to make this normality assumption. So when we get our estimated values of B1 hat, or of B1, which is B1 hat, and the standard error of B1 hat, we can construct the t-test statistic in exactly the same way as we did last week. So we just take our estimated value on the numerator, and we take the standard error of the estimated value on the denominator. So exactly the same interpretation as we had before. We're looking just at the sort of association between x and y. And if it's large relative to the standard error, then t is going to be large in absolute value, of course. And if it's small, if this slope parameter is small relative to the standard error, then this t statistic is going to be very close to 0. And we can do our hypothesis test exactly the same way. We choose our significance level alpha, and we look at the absolute value of this t statistic and compare it to this critical value, which is going to be a function of our significance level alpha and the sample size of interest. And so if our observed test statistic is greater than the critical value, then we would reject our null hypothesis. And so we would say there is a significant linear relationship between these two variables, and otherwise we would not reject H0, so we would not have any evidence of a linear relationship between these two variables. And we can calculate our p-values and our confidence intervals as the same way we did in the one sample t-test. I'm going to leave out the formulas for that, but it's something that's we can do in SPSS. All right, so I'm going to go back to my IMPC data example. So I found the best fit, our linear regression line for the relationship between creatinine and total cholesterol. So if you do the linear regression, you get an estimated slope of 199.74. So if we go back to our original interpretation of B1, that would suggest that an increase of 1 in creatinine, so 1 milligram per deciliter, would correspond to an increase in 199.74 in total cholesterol. Well, so this goes exactly to the question that Josie asked a few minutes ago. Well, if you look at an increase of 1 in creatinine, that would go way beyond the scope of the observed values of creatinine. You can see we only go from about 0.1 to a little over 0.3, so a change of 0.2. And if we look on total cholesterol, a change in, we don't even have, we wouldn't be able to characterize a change in 200 milligrams per deciliter in total cholesterol. That wouldn't even fall within this chart. And so sometimes the base sort of interpretation of this B1 isn't appropriate, but the good thing is we can scale everything down. So let's say I divided my change in x by 10, and I divided my change in y, so I divided this B1 parameter by 10 as well. Then you can interpret in the same way. So you say, if you see an increase in 0.1 milligrams per deciliter of creatinine, that would correspond to an average increase of this divided by 10, so 19.974 milligrams per deciliter of total cholesterol. So that's the good thing about linear regression, is that you can scale your change in x and y variable by whatever quantity you want, just as long as you're scaling the x and the y by the same quantity. Okay, so if we look at the actual hypothesis test from our data example, so yes, we had our B1 hat is 199.74. We get a standard error for B1 hat as 21.69. We have a fairly large sample size of 1,471, and let's test this at significance level alpha equals 0.05. So if we calculate our test statistic, t, we end up with 9.21. And if we look at our critical value of t, we get 1.65. And as we can see, our obtained value of t is 9.21, much larger than 1.65. And so we would reject our null hypothesis. So that would imply that we have evidence of a linear association between creatinine and total cholesterol. One important thing to point out is that we can never say anything causal when we find a significant association. We can't say that the x variable is causing y to change. All we find is an association. So if we go and calculate our p-values and our confidence intervals, well, p-value is very small. It's less than 10 to the minus 16. And if we calculate our 95% confidence interval, we get 157 to 242. And so you can, so again, because our null hypothesis is that B1 is equal to 0, we would compare this confidence interval to the value 0. So if it overlaps with 0, then we would not reject our null hypothesis. And in this case, since it does not overlap with 0, we do reject our null hypothesis. All right, so I had mentioned we do have to make a few assumptions when we perform linear regression. So there was the one that I talked about earlier with the x values being fixed, which very often gets sort of pushed aside. But there are 4 additional assumptions, 4 main assumptions that we have to make. The first one is quite obvious. We have to assume that there is some underlying linear relationship between these two variables. And the second one we make, I also mentioned, is the normality assumption. So basically we're assuming, so the way I characterized it before was that we put a normal distribution on our error terms, but it's equivalent to saying that, okay, for a given value of x, the values of y follow a normal distribution. So that would just mean that, let's say we look at the value of creatinine 0.2, and we just look at all the values that fall exactly on 0.2. We look at the distribution of those values, that should follow a normal distribution. And it should follow the same normal distribution if we look over at values of creatinine at 0.15, and the same over here at 0.25. So it just means that another way we say this is that y follows a normal distribution conditional on x, when you take x into account. Another important assumption that we have to make is one that we make very often, the independence assumption, that values of one observation do not influence the values of another observation. There are methods out there, like repeated measures methods, that can account for that. And in regression, there's a specific model called a random effects model, which we can use to account for that. That's sort of beyond the scope of this seminar today. And our last assumption is also another important one. And we assume this, the assumption is formed through this very weird word, which is homoscedasticity, which means that the variance of y does not change over the values of x. And so I had alluded to that before. That just means that when you're looking at the spread of these values around the fitted line, the variance of that spread does not change as we pass from one side of our x variable to the other side. Okay. So one way that we can check our assumptions, and the most common way we check our assumptions in linear regression, is to look at the residuals. So we look at sort of the leftover values after we've fitted the line. And our most basic tool is looking at a scatter plot of the fitted values versus the residuals. So we put our fitted values on the horizontal axis, and we put our residuals on the vertical axis. So the point is that because we've included a variable in our model that we think is going to do a good job of explaining variation in this variable, well, if that's the case, then we wouldn't want to see any sort of pattern in this residual plot. So two things that could manifest in the residual plot is we could see that we do in fact violate our assumption of constant variance, or we could also have some variables missing from our model that turn out to be important in explaining variation in the outcome variable. And we can also check the distribution of residuals to see if the assumption of normality is met. So here's a residual plot for the IMPC data. So we have our fitted values, so just those yi hats on the horizontal axis, and we have the residuals on the vertical axis. And so really this is just something that you do visually. You can look at the variance of these residuals. So again, you want to see, is the spread of these residuals around the value 0 sort of constant as we go across the different fitted values? So of course, a residual of 0 means that your observed point is very, very close to the fitted regression line. So yeah, and you can also look for kind of like a pattern, see if, to see if these residuals are sort of increasing or decreasing. And in this example, this is actually a pretty good residual plot. I don't really see any discernible pattern. Maybe there's a tiny, tiny decrease in the residuals as you're going higher in the fitted values, but as far as real data goes, this is a pretty good residual plot. But here are two examples of some very, very bad residual plots. So the one on the left here, you can see it has this sort of U shape to it. Okay, so when you see a kind of change, almost a change in the mean of the residuals as you go over your fitted values, that often means that there is a variable, an important variable missing in your model. And when you see a pattern like this means that there is in fact a nonlinear variable missing in your model. So again, this is all just simulated data. And as it turns out, there is a quadratic variable, so a nonlinear variable that is missing in this example. And so the residual plot is not going to look like a nice sort of block with constant variance. On the right side here, we have another very bad residual plot. And this is displaying what you get if you don't have the assumption of constant variance met. So on the left side here, you can see that the residuals are very, very close together, and as you go over to the right, the residuals are very, very spread apart. And so this is actually a very common thing that you would see in linear regression. You see sort of this funnel shape in the residuals as you increase your fitted values. So what do you do if you have a bad residual plot? Well, it's hard to say exactly. In reality, sometimes you just have to kind of play around, experiment a little. You can add additional variables to your model, so that would get us into multiple linear regression. So there might be other important variables that you think could explain variation in your outcome variable. You could add higher order terms to the model. So that's what I was talking about here in this left chart. So for example, if you had age as your predictor variable, as your variable on the horizontal axis, then you could actually add the square of age as an additional predictor in your model. And as it turns out, even if you square a variable or take a cube or take a square root or something like that, and you just add it as an additional predictor variable in your model, this is still considered linear regression. Even though you're looking at a non-linear variable, it's still considered to be linear regression, and you can use the same formulas as you did before. One of the most common things that we do, however, is we can transform our outcome variable, our y variable. So by transform, I mean we just apply some mathematical function to the variable, and then we run our linear regression as we would before. So some examples of transformations include taking the log of our outcome variable, or we could take the square root of our outcome variable. However, you do have to be a little bit careful when you do this, as this is going to change the interpretation of your B1 parameter. So if you take the log, then the interpretation of B1, instead of being additive, is going to be multiplicative. So it's going to be like every time you increase B1 by 1 unit, you're actually going to multiply your y variable by a certain constant. But the most important thing to remember when you're doing this, if you're trying out a whole bunch of different models, is, okay, so what I wrote here is don't look at the p-value during this process. I don't mean that literally. Obviously, you're going to look at the p-value, but we're humans. We want to see if things are significant or not. But what I mean by this is that you should not let the p-value influence your decision as to what model you're going to choose as your final model. You should only be choosing your final model based on trying to fulfill your model assumptions as good as possible. So if you don't do that, if you choose your model based on the p-value, that's exactly the definition of what I call p-hacking, which is something that it happens very often in today's literature. Okay, so on the left here, I have this same residual plot as I showed before with the non-constant variance. So if I were to first take the log of my y variable and then run a linear regression on that, then my residual plot would look more like this. So a much better looking residual plot. Maybe the variance on either end is shrinking a little bit, but sometimes that's about the best you can do. But compared to what we had before, this is a pretty good residual plot. All right, so that's simple linear regression. That's when we look at just two variables, one sort of predictive variable and an outcome variable. So before I move on to multiple regression, do we have any questions about simple linear regression?
There we go. So I just want to clarify something. You mentioned at one point, and maybe I misunderstood, is that you assume that your values are independent of one another, i.e. one doesn't influence the other in order to do this. Is that correct?
Yes.
Okay.
Yeah.
But maybe I'm misunderstanding this, but what if there is a causal relationship between the two? So I'm thinking a gene and a transcription factor. One does influence the other.
So what I mean is, So I'm kind of confused as to what exactly you mean by that, because if you're talking about different individuals, the assumption of independence is on different individuals, right? Not between your variables. So it's not independence between X and Y,
Okay.
because that's exactly what you're trying to investigate. It's independence between one individual's measurements and another individual's measurements.
Okay. Sorry.
Yeah.
And one more question. Often I see a Spearman and a Pearson. Are they very different from one another?
Yes and no. So the Pearson works very well on data where both X and Y follow a normal distribution. And a Spearman correlation coefficient is something that you use when you have kind of a weird distribution in your data, like something non-normal. And as it turns out, what Spearman correlation is you change every observation to a rank. So you forget about the actual value of your two variables. You just call the highest value, you call that 1. The second highest value, you call that 2. The lowest value, you call that n. So you do that for both your variables. And then on those ranks, you actually calculate the Pearson correlation. You just plug it into the Pearson correlation coefficient. So that's going to give you a measure of correlation, which is similar to Pearson correlation, but it's more robust to departures from a normal distribution.
Okay. So I just want to make sure that I understood correctly in that you cannot use linear regression if you don't have a continuous variable, say on the x-axis. If you were to have...
So the only variable that needs to be continuous is the y variable.
So the x can be independent.
So the x can be categorical, and it is still linear regression. So as I had mentioned, like the t-test is a very special case of linear regression. So if you have a continuous variable for your y variable and you have a binary variable, just say a 0, 1 variable on your x-axis, you can actually just do everything exactly as I mentioned here, and the result will be exactly equivalent to a t-test. Yeah. And you can have mixes of a mix of continuous variables with categorical variables.
So just a question regarding fixing your residual values by making them into log. How does that change your model? Are you also doing the same there? I think I'm just not.
So really the only thing it changes is just the interpretation of your parameters. So you're still going to have this sort of this model right here, but what you're going to have is on the left side here, let's say you're doing a log transformation, you're going to have log of yi is equal to beta 0 plus beta 1 xi. And so you are going to get different values for beta 0 and beta 1 when you do that. But that's okay because now the interpretation is different. So this beta 1 value this b1 value is going to be multiplicative. So instead of so before, when we had a linear relationship between the two, we had a unit increase in our x variable meant that you would add a certain value to your y variable. Well, if you look on the on the log scale of your y variable, then increasing your x variable by 1 unit would multiply your y value. So you're going to end up with like an exponential relationship. But it's still linear regression. So we can still use the same formulas as we did before to find values of beta 0, b0, and b1, but the actual values are going to turn out to be different.
Quick question. Are you going to review binary logistic regression at some point?
So the question is, are we going to review binary logistic regression? No, that's unfortunately beyond the scope of this series, but yeah, that's something that's, from my department in epidemiology is very, very important. But we only have so much time, unfortunately. We have another one over here.
I have a question about the confidence interval.
Sure.
And you have calculated that is 95%, and after that you have written numbers. What does it mean, these two numbers, like 242
These ones?
or 100? Yes, exactly.
So this is just sort of, basically any confidence interval can be interpreted in the same way. All you're doing is you're just saying, okay, well, we got an estimated value for B1, but we acknowledge that that's probably not exactly the true value because there is sampling variability. And so all we do is we use this t-distribution to construct kind of a viable range, so from a lower value to an upper value, that we're somewhat confident the true parameter value falls into. So, and the width of this confidence interval is going to change depending on the height of our confidence. So if we had, let's say, a 99% confidence interval, then this would actually be a wider confidence interval. Because the wider you get, the more confident you are that the true value of the parameter is contained within that interval. So yeah, all it is just kind of like a viable range for the true parameter value. Yeah. All right, so yes, up till now we've only had one predictor variable and our outcome variable. So that was simple linear regression, and now we're going to look at multiple linear regression. I'm just going to go look at this very quickly because things in multiple regression can get a little bit more complicated. But so it's very, very similar to simple linear regression, but so now we actually have more than one predictor variable. So we still only have a single response variable y, but we want to look at the sort of joint effect of a bunch of predictor variables on this outcome variable y. So for example, if we had 3 predictor variables, so we'll just say x1, x2, and x3. So I now have like a double subscript on each of our x's. So this just means the first individual's observation of the first variable, the second individual's observation of the first variable, et cetera, et cetera. And this is just all the individual's observations for the second variable, all the individual's observations for the third variable. So we still assume that there are n individuals. And this is how we set up our regression model. So we have our outcome variable yi is a function of, again, an intercept parameter, and we put each of our variables into the model, and we have an individual slope term for each variable. And then we have our leftover sort of error term epsilon. So the main parameters of interest here are going to be just B1, B2, and B3. And so these are going to measure the associations of each of those 3 predictor variables on the outcome variable y. So we still have to make all the assumptions as we did before. So have to have linear relationship, we have to have normality, independence, constant variance, that sort of thing. We also have to have an additional assumption that these 3 predictor variables are not too correlated with each other. So why would we want to do multiple regression in the first place? Well, it could be that we're interested in the joint effect of these predictor variables on this outcome variable. And the reason we would put everything into a model is that the estimated effects are going to be different when we do that than if we had just run a series of separate linear regressions for each x and y pair. And turns out that you tend to get better estimates. You get more efficient estimates when you put things together in a model. That's only true to some extent. Of course, you have to take your sample size into consideration, but in general, if you have, say, a large enough sample size, then putting more things into your model will often help you out in terms of efficiency. So one reason we would do multiple regressions, so let's say even if you are only interested in two variables, in an x variable and a y variable, you can still include additional variables as predictors in your model to adjust for those other variables. So there are other variables like confounding variables where there's an external variable that affects both your sort of predictor variable and your outcome variable. And if you don't adjust for that variable, then you would have bias in your estimates. So a good example is in our total cholesterol versus creatinine example. We could include the mouse's body weight as an additional variable in the model. And just by doing that, and just by finding our model parameters, we have adjusted for mouse body weight in this relationship between total cholesterol and creatinine. So yeah, this is something, when you see in literature, when they're talking about adjusting, we adjusted for age, we adjusted for sex, that sort of thing, this is just what they mean. It just means they took that variable into account in the model. And lastly, again, even if we're only interested in the relationship between two variables, between an x and a y, and if we don't even think that there are variables that could cause bias in our estimates, we could still include other variables in that model to improve the efficiency of the estimates of association. And by efficiency, I just mean we end up getting smaller standard errors for that B1 parameter, which means we're more likely to reject the null hypothesis if the null hypothesis is truly false. So we have interpretations for the different slope parameters, and they're very similar to in simple linear regression, but we have to take one extra thing into account. So if we look at just the first one, so the slope parameter for the first variable, we're looking at the effect of that first variable x1 on y, conditional on all other variables. So another way of saying that is that we're looking at the estimated increase in the response of y associated with an increase of exactly 1 unit of xi when everything else is held constant. So if you held x2 and x3 just at a constant value, then b1 would be that rate of change. And we have likewise interpretations for b2 and b3. So when it comes to estimating these parameters in multiple linear regression, that's where we start to get a little bit more complicated. We really need to use a computer to do that if we're looking at more than two variables and we're looking at a large sample size. And it also requires matrix algebra, and so that's definitely beyond the scope of this seminar series. So I'll just say that, again, exact formulas exist to find the best fit for these parameters, but I'm just not presenting them here. And same thing for the standard errors for each of our parameters. They're a little bit more complicated to get, but there are still nice formulas that exist out there for finding those standard errors. All right, so we can do hypothesis testing in multiple linear regression, and we can do it in several different ways. There's a way where we can test like the whole model and see whether or not all the variables sort of jointly have a significant impact on the outcome variable. But I'm just going to focus on testing these individual parameters. So in our case with 3 predictor variables, we have j is equal to 1, 2, and 3. And so for each of those predictor variables, we have our null hypothesis is that the slope term beta j is equal to 0, and our alternate hypothesis is that bj is not equal to 0, so that there is a significant linear relationship between the jth predictor variable and the outcome variable. And once again, it turns out that we can just use a simple t-test to test this hypothesis. So we have our estimate for the jth parameter and this divided by the standard error. So if we look back to our IMPC data, so I just present an example where we want to look at how total cholesterol changes with respect to 3 variables that I happen to have in my data set. So creatinine again, glucose, and mouse body weight. So our regression model, I had the X's put in before, but sometimes we write it in this way where we just put the actual name of the variable that we're studying. So we say that our yi is just a sum of our B1 times creatinine plus B2 times glucose plus B3 times weight, and our intercept term as before. And so if you plug this all into your software, you're going to get, so in the first column here I have the estimates of each of these B1, B2, B3. And one thing that you'll notice is that the value of B1 for creatinine is much smaller than it was when we only looked at creatinine by itself. So often that happens when you include additional variables in your model. Your model will automatically detect that variation in your outcome variable can be better explained by other variables, and so it's going to adjust the slope parameter for your first variable accordingly. And that's exactly what happened here. And so when you do this, you also are going to get your standard errors right out of the model, and you're going to get your individual p-values. So this is just for doing a hypothesis test separately for each of these 3 variables. So as you can see, the p-value for creatinine also is smaller, quite a bit smaller, it's larger than what it was before. And the p-value for this weight variable is very, very, very small, like 10 to the minus 113. So all 3 of our variables are significant here. So once you have that, something that's very common is you can just plug the estimated values of B1, B2, and B3 right into the model and write your model out this way. So that if you had say a new mouse and you wanted to predict their total cholesterol level, you could just plug in their values of creatinine, glucose, and weight into here and just calculate this formula and get a predicted or estimated value for that mouse's total cholesterol. Okay, so I just did a very simple introduction to multiple regression. I'll show you a little bit more in the SPSS example. But just before I do, I'll give my take-home message. So yes, regression is a very, very powerful tool. It's super versatile. There's a wide range of literature on regression, and there really is a lot that you have to take into account when you run a regression analysis. But yeah, as I said, it's something that I use all the time, and I think that you should use too. That being said, you do have to do a very thorough investigation of your model assumptions to make sure that that whatever you claim from your regression model is statistically sound. There are lots of assumptions to make, but there are also lots of other models out there that exist if your assumptions are not met. So if you have non-constant variance, and let's say you tried a couple of transformations and that didn't work well either, well, there's a whole new method called weighted least squares you can use for that. If you have non-normal data, well, there's a huge branch of mathematics out there called generalized linear models where you assume different distributions for your outcome variable. And if you don't have independence of your observations, then you have something called a random effects model. So there's a lot of room for choosing a model in linear regression, what variables you include, what transformations you do, that sort of thing. But I just want to reiterate that you always want to make your choice of model based on good statistical principles, never based on the resulting p-values you get from the model. All right, so that's the lecture for now. So as usual, I'll do a quick question round before I go into the SPSS tutorial.
So when doing a multiple test or a multiple regression, would it be appropriate to include a multiple test correction in your p-values?
Yes, absolutely. So something I haven't talked about yet is when you do a large number of comparisons and look at a large number of p-values, the more p-values you look at, the more likely you are to see a false positive in your significant p-values. And so usually we will do what's called a multiple testing regression, which I'm thinking of talking about in our last lecture. But yes, definitely that's something you should be doing.
So I have two questions. My first question is, do you ever transform the x variables before doing regression, or is it only the outcome that you can transform?
Sometimes you do transform the x variable. And again, you just have to be careful because it is going to change the interpretation of your model. And also, if you remember, I had talked about assuming the x variable being fixed, and if you ignore possible measurement error, it can introduce bias in your model. I'm not exactly sure what the result would be if you transform your x variable. It's not obvious to me what the result would be in that case. But yeah, it's something that people do, for sure.
And my second question is, you mentioned that when you do multiple regression, the variables that you put in it should not be correlated. Is that correct?
They shouldn't be strongly correlated.
So how can we tell that? Because like the example you gave us, as you know, weight and glucose can be very correlated.
Yeah.
So
there's a whole, this goes to testing your assumptions. There's something called a variance inflation factor I didn't talk about today. So if your predictor variables are very strongly correlated, it turns out that the variance and therefore the standard errors of those individual parameters are going to be inflated. They're going to be artificially high, and it's going to make it difficult to reject your null hypothesis. And so you can calculate this thing called the variance inflation factor, which basically the higher it is, the worse your collinear, what we call multicollinearity. So the higher the variance inflation factor, the worse the multicollinearity. And basically you give like an arbitrary cutoff to that factor, and if it's above that value, then you say you have a problem with collinearity, and if it's below that value, then you don't have a problem. But like many things in statistics, it's kind of arbitrary where you choose your threshold. But yeah, there are diagnostics for checking that sort of thing out. Yeah.
thank you.
Yeah, it's a more naive question, but I was wondering if you use the multiple regression and you want to test, as you said, like creatinine and glucose and weight, and you said you could use those kind of tests in epidemiology to say that your result has been matched for age or sex or whatever. What kind of result do you expect to say that it is independent or dependent on the weight? Or it wasn't clear to me if the two variables you were testing, if in the end you can say this is dependent or independent on.
So really we can't say anything whatsoever about dependence or independence. That is a more broad question because in linear regression we're only investigating if there's a linear relationship between variables. There could be a very, very complicated nonlinear relationship between those two variables that you haven't captured in your model. And so if just because you get a non-significant finding doesn't really mean anything about independence. If you do, I guess if you do find something significant, you can say that they're not independent, but you can never really say that they are independent. Okay, so I'm going to go on to the SPSS tutorial. Okay, so yes, I have same data set that I used during my talk. So we just have some clinical blood chemistry measures from the IMPC data. So I'm just going to show you quickly how to do a linear regression. Actually, first I'm going to show you how to calculate the Pearson's correlation between all of these variables. So it's very simple. You just click on Analyze like usual. You go to Correlate, and you click on Bivariate. And then you have your list of variables that you could include, and you're basically going to find the correlation between every single pair of variables in the data that you include. So I'm just going to put everything in to the box on the right, and I'm just going to click OK. And so we get something that's called the correlation matrix. And so all we get is just, if we look at a column and a row, we have a variable, so in this case bilirubin and glucose. And you can see that the correlation, the Pearson correlation here is 0.147. If we look at creatinine and urea, we can see that the correlation is 0.098. And actually, SPSS does a statistical hypothesis test on this correlation parameter, and they give the p-value for that correlation parameter. So just this sig two-tailed. So in this case, between total cholesterol and bilirubin, that would give you a p-value of 0.001. And as it turns out, this test is exactly equivalent to doing a simple linear regression. So if we had just done a simple linear regression between total cholesterol and bilirubin, we would have got exactly the same p-value. Once you get into multiple regression, then this isn't true anymore. It gets a little bit more complicated. But yeah, so this is a very good way to start out when you're looking at your data, just to see if certain things are strongly correlated with other things. All right, so I'll show you how to do linear regression. So again, same menu as we usually go to: analyze, regression, and linear. So the thing that we put on the top here, the dependent variable, that's our y variable, or our outcome variable. So I'll do the same thing I did in the lecture, use total cholesterol as the outcome variable, and I'll use creatinine and glucose as independent, and also mouse body weight as independent variables. And before I run this, you can click on the statistics button on the right to get it to output different statistics, different measures. And so it already has my estimates, and I'm also going to ask it to give me some confidence intervals, and you can just choose the significance level of your confidence interval. So I just click continue and OK, and then it should. Actually, there was one more thing that I forgot that I want to include here. So I'm just going to do that same thing again. But you can also get it to output a residual plot as you're doing this. So you can check your residuals right away. So you can click on this plots option. And so you can specify what types of residuals you want, or fitted values on the x and the y axes. So as we did before, on my y-axis, I want our residuals. And so that's this thing called z-resid. And then on the horizontal axis, I want our predicted values, or our fitted values. So that's just called z-pred. So I'll put that on the horizontal axis. I click continue, and then OK. So this is just going to take a second to run. OK, there it is. All right, so you get a few different things in your output. I'm just going to focus on this third table here, this coefficients table. So this is the same thing as what we saw in, I think it was the second or third last slide. So we just have, in the rows, we have our different variables. We have creatinine, glucose, and mouse body weight. We also have a row that's called constant. So that's the intercept term B0. So usually, like, it's something that you always have to have there, but we usually just sort of ignore. And the first column gives us the estimated parameter values for B. So same as we saw before, 67.9, 0.13 for glucose, 3.4 for mouse body weight. We have our standard errors. And then, as usual, under the sig column, we have our p-values. Again, they're rounded up, but you can change this to output some additional decimal points if you want. And then you also have your 95% confidence intervals on the right side. So for creatinine, we have 29 to 106. Glucose, we have 0.117 to 0.161. So yeah, once you do that, you can, if you want, you can actually copy this table and paste it into a Word document, or you can export it into a Word document and just include it right in your report or your publication or whatever you're doing. So it's very convenient in that way. So lastly, I am just going to look at a scatter plot of our residuals. So in this case, I look at a very specific type of residual. So before, I just looked at predicted values versus residuals. So in SPSS, it actually scales your residuals. It scales them down so that they have a mean. So the residuals are centered at 0. They have a mean of 0, and they have a standard deviation of 1. And that's just so that you can compare residual plots between different variables. But sort of the relationship between the predicted values and residuals are not going to change at all when you do this. So one thing, so usually we look at residuals in relation to the value 0. So it might be useful to plot a horizontal line at 0. So in order to do that, I can just double click on our plots. It opens up this chart editor. And there's an icon here for a horizontal line that you can click on. It opens up this additional window where you can just choose the position of this horizontal line. So I'm going to put it at 0. So I just click apply. It moves it down to 0. Then I can just close everything down, and it's automatically going to replot this chart with a horizontal line at 0. All right, so this residual plot, it's not the best. Could be better. You know, it looks like maybe there's shrinking variance on the right side here, and in general, it does sort of look like the residuals are maybe decreasing a tiny bit as you go from left to right. So there could be other things you could try. Maybe you can include additional variables in the model to get a better model. This doesn't look bad enough that I would try a transformation, but you never know. You could always try something like that. But so in terms of, as far as real data goes, this isn't a bad residual plot. Really, when you see a bad residual plot, you know right away. You'll see something like a funnel shape or a curve in your residuals. All right, so that was everything I wanted to show you in this SPSS example. So any questions on the tutorial? Maybe you're all tired and you just want to go. I wouldn't blame you. Okay, thank you.